Reality itself contains contradictions that can unravel our deepest laws of physics. These are not simple puzzles, but profound paradoxes. And over the next 30 explorations, you will gain a new framework for questioning the very nature of the universe. We will confront a cat that is both alive and dead, and ask why the cosmos is so silent if it should be teeming with life. By the end, your understanding of time, space, and existence will be fundamentally expanded. What does it truly mean for something to be impossible? These contradictions are not flaws in the universe, but rather vital clues to its true structure. For centuries, paradoxes have served as the most powerful engines of scientific discovery. They begin as seemingly impossible riddles, but they expose the exact point where our current understanding breaks down. The ancient philosopher Zeno presented a paradox about a race between a tortoise and a hero, arguing that motion itself was an illusion because to reach a destination, one must first travel half the remaining distance, then half of that new distance, and so on forever. This logical puzzle forced thinkers to grapple with the concepts of infinity and the infinitesimal, ideas that would later become cornerstones of calculus. Centuries later, a problem known as the ultraviolet catastrophe revealed a fatal flaw in classical physics, predicting that a hot object should radiate infinite energy, which was clearly absurd. This single contradiction could not be ignored, and the desperate search for an answer led directly to the birth of quantum mechanics, a theory that redefined reality at the smallest scales. Each paradox is a flashing warning light on the dashboard of our knowledge, signaling a gap between what we think we know and what actually is. By bravely confronting these uncomfortable contradictions, scientists are pushed to refine old models, propose radical new dimensions of space, and even entertain ideas as vast as the multiverse. Our journey through 30 of these mind-bending puzzles is not a search for tidy solutions, but an embrace of the profound questions that have the power to completely redefine our place in the cosmos. The true power of a paradox lies in its stubborn refusal to be easily dismissed. In physics, a paradox is not merely a tricky puzzle or an unsolved mystery. It is something far more potent and revealing. It is a scenario often crafted as a precise thought experiment, where the rigorous application of our most trusted scientific laws and flawless logic leads us directly to a conclusion that is absurd, contradictory, or fundamentally impossible. This is the critical difference. A mystery is a gap in our knowledge, while a paradox is a glaring spotlight on a crack in the very foundation of our understanding. It creates a conflict, a direct confrontation between what our theories predict and what our intuition screams must be true, or even worse, a battle between two of our most successful and well-supported theories themselves. Consider the monumental clash between the two pillars of modern physics. General relativity masterfully describes the universe on the grandest scales, governing the dance of galaxies and the curvature of spacetime itself. Quantum mechanics, with equal brilliance, dictates the bizarre rules of the subatomic world. Yet, when we try to apply both theories to the same extreme event, like the conditions inside a black hole or at the very beginning of the universe, they produce completely incompatible, mutually exclusive predictions. This is not an error in calculation. It is a paradox, an illuminating failure that screams our current description of reality is incomplete. Recognizing this definition transforms our entire journey. Each paradox we encounter is not a flaw in the universe's design, but a flaw in our current map of that universe. They are not signs that nature is broken, but brilliant signposts pointing directly to where our human-made models break down. This crucial distinction turns our list of 30 mind-bending concepts from a catalogue of confusing impossibilities into a guided tour of the very frontiers of human knowledge, showing us exactly where the next great leap in understanding must occur. But of all the paradoxes that challenge our understanding of time, none is more personal or more unsettling than the Grandfather Paradox. This thought experiment strips away the glamour of time travel to reveal a terrifying logical snare. The premise is brutally simple. Suppose you build a machine and journey back to a time before your parents were born. You locate your own grandfather, and through some action, you prevent him from ever meeting your grandmother. The consequence is immediate and absolute. Without that meeting, your parent is never conceived, and therefore you are never born. But if you were never born, who then traveled back in time to alter history? The very act that erased your existence also erases the cause of the act itself, trapping the entire scenario in a loop of impossible logic. It is a perfect contradiction, a causal knot that cannot be untied within a single, consistent timeline. This paradox does more than just highlight a problem with time machines. It strikes at the very heart of cause and effect, the principle that every event must have a preceding cause. Here, the effect destroys its own cause, creating a void where reality itself seems to short-circuit. For physicists and philosophers, this is not just a plot for science fiction. It is a rigorous tool used to test different models of time. One compelling solution is known as the Novikov self-consistency principle. It proposes a universe with a single, unchangeable timeline. Under this rule, any attempt by a time traveler to alter a past event would inevitably fail. Your actions in the past are not new interventions. They are, and always have been, part of recorded history. Perhaps you travel back with the intent to stop your grandfather, but a sudden slip on a banana peel or a surprising change of heart ensures that your journey actually causes the very event you sought to prevent. The timeline protects itself, enforcing a kind of cosmic destiny where free will is an illusion for the traveler. A radically different answer emerges from the many worlds interpretation of quantum mechanics. In this view, the moment you arrive in the past and take an action that changes a key event, the universe does not rewrite its own history. Instead, it splits. A new parallel branch of reality is created, one where your grandfather's life took a different turn and you were never born, but in your original branch, your history remains intact. You are a visitor from another world, and your actions have consequences only for the new timeline you created, not for your own past. This paradox ultimately forces a profound question upon us. Is the past a fixed record, a completed book where every word is already written in indelible ink? Or is it a fluid narrative open to editing and revision, with our future selves potentially holding the pen? The Grandfather Paradox suggests that if time travel to the past is ever possible, our universe must operate under rules far stranger and more restrictive than we have ever imagined, rules that either lock history in place or endlessly multiply it. The silence of the cosmos is perhaps the loudest paradox we have ever encountered. On a clear, dark night, the sheer number of stars overhead hints at an almost unimaginable scale. Our galaxy alone contains hundreds of billions of stars, and most of those stars are now believed to host planets. With so many worlds, and with the universe being nearly 14 billion years old, it seems statistically inevitable that life, and even intelligent, technological life, should have arisen many times over. The numbers are overwhelmingly in favor of a crowded, vibrant galaxy. And yet, when we listen, we hear nothing but the natural radio whisper of celestial bodies. When we look, we see no megastructures, no interstellar probes, no unmistakable signs of a galactic civilization. This glaring contradiction between high probability and zero evidence is the Fermi Paradox, named for the physicist Enrico Fermi, who famously asked, "But where is everybody?" It is a question that challenges not just our astronomy, but our deepest assumptions about life, intelligence, and destiny. One chilling resolution is known as the dark forest hypothesis. Imagine the cosmos not as a welcoming community, but as a vast, dark forest where every civilization is a hidden hunter. In this view, broadcasting your location is the ultimate folly. Any other civilization you might detect could see you as a threat or a resource, and the safest strategy is to remain completely silent and utterly hidden, ready to strike at any sign of another. The great silence, then, is not an absence of life, but a universe holding its breath. Another profound answer is the concept of the great filter. This idea suggests that the evolution from simple chemistry to a spacefaring civilization requires passing through a series of extremely difficult steps, like a series of gates. One of these steps, the great filter, is so improbable that it almost always stops progress in its tracks. The terrifying implication is that we do not know if this filter is behind us, perhaps in the miraculous jump from non-living molecules to the first simple cell, or if it still lies ahead of us in our future, a challenge so severe that no civilization we have ever detected has managed to survive it. This paradox ultimately forces a humbling reflection. Are we precocious, arriving early in a universe that will one day teem with life we cannot yet see? Or are we tragically alone, having won a cosmic lottery whose final prize remains unknown? The silent stars offer no answer, only a profound question about the rarity and fragility of every whisper of intelligence in the dark. A sealed box becomes the stage for the most famous paradox in all of physics. Inside, a cat rests alongside a single radioactive atom, a Geiger counter, and a vial of lethal poison. The mechanism is simple, yet its implications are world-shattering. If the atom decays, the counter clicks, a hammer falls, the vial shatters, and the cat is lost. According to the rules of quantum mechanics, that solitary atom does not have a definite state until it is observed. It exists in a ghostly blend of possibilities, a superposition of both decayed and not decayed. And because the fate of the cat is tied directly to the state of the atom, the entire system becomes entangled in this quantum uncertainty. Until someone lifts the lid and looks, the cat, in the strictest mathematical sense of the theory, must be considered both alive and dead. This was not a proposal for a real experiment, but a powerful critique. The physicist Erwin Schrödinger created this unsettling scenario in 1935 to expose what he saw as an absurdity in the prevailing Copenhagen interpretation of quantum mechanics. His point was devastating. How could the bizarre, probabilistic rules that govern particles in the subatomic world possibly apply to a living, breathing creature in our familiar, classical world? The thought experiment forces a confrontation. It asks where the boundary lies between the quantum realm and our everyday reality. At what exact point does the cloud of probabilities collapse into a single, definite outcome? Is it the click of the Geiger counter, the breaking of the glass, or is it the observation by a conscious mind? This last possibility, that consciousness itself causes the wave function to collapse, is one of the most debated and profound ideas in modern science. It suggests a universe where reality is not fixed until it is perceived, weaving the observer inextricably into the fabric of existence. Schrödinger's cat ultimately bridges the chasm between the invisible weirdness of the quantum and the solid certainty of our lived experience, challenging us to accept that the universe may not make a final decision about what is real until we are there to see it. Time itself becomes a relative experience in the story of two identical siblings. This is the twin paradox, a thought experiment that transforms a family reunion into a profound demonstration of Einstein's special relativity. One twin boards a spacecraft capable of traveling at an enormous fraction of light speed, journeying to a distant star and back. The other stays comfortably at home. According to the theory, time passes more slowly for the moving twin. The high-speed traveler experiences time dilation, where every second on their clock ticks just a bit slower relative to the clock on Earth. The result is dramatic and seemingly impossible. When the traveling twin returns after what felt like a few years, they step out of the ship to find their Earth-bound sibling has aged decades. One is young, the other old, separated by a gulf of time created not by biology but by velocity. Yet here lies the apparent contradiction. Motion is relative, is it not? From the perspective of the astronaut twin, wasn't it the Earth that hurtled away at near light speed and then returned? Shouldn't the Earth twin, from this viewpoint, be the younger one? The paradox seems to suggest that each sibling should see the other as younger, a logical impossibility. The resolution shatters our intuitive sense of symmetry. The key is that the traveling twin's journey is not a story of constant, unchanging motion. To begin the trip, to turn around at the distant star, and to finally land back on Earth, the spacecraft must accelerate and decelerate. It changes its state of motion, feeling palpable forces. The stay-at-home twin, however, remains in a single, unaccelerated frame of reference throughout. This difference is absolutely critical. The laws of special relativity, which state that all constant velocity motion is relative, apply only to these unaccelerated frames. The moment one twin feels the push of acceleration, their experience of reality is fundamentally different. Their path through the four-dimensional fabric of spacetime is not equivalent. While both twins can rightfully claim the other was moving during the constant speed legs of the journey, only the traveling twin undergoes the physical experience of changing that motion to come home. This asymmetry breaks the paradox and dictates who truly ages less. This is not merely a philosophical argument. It is a confirmed, measurable fact of our universe. We have tested this with extraordinary precision using not human twins, but the most accurate clocks ever built. Atomic clocks flown on airplanes or placed on fast-moving satellites like those in the Global Positioning System network tick at a subtly different rate than their counterparts on the ground. Engineers must account for these relativistic time shifts, both from the satellite's speed and their position in Earth's gravity well. Otherwise, the GPS in your phone would fail within minutes. The system would be useless without correcting for Einstein's laws. The twin paradox, therefore, moves from a fascinating puzzle to an operational truth of modern technology. It proves that time is not a universal metronome ticking the same for everyone, everywhere. It is a flexible, personal dimension woven inseparably with space, its passage shaped by how we move through the cosmos. The traveler returns not just to a changed world, but as living proof that the future is a destination we do not all reach at the same speed. The darkness of a clear night sky holds a secret that once threatened to unravel our entire picture of the cosmos. This is Olbers Paradox, named for the astronomer who formalized a question so simple a child could ask it, yet so profound it reshaped modern cosmology. If the universe is infinite, static, and filled with an endless number of stars, then every single line you draw from your eye out into space should eventually land directly on the surface of a star. There should be no gaps, no darkness between the points of light. Just as in a dense, ancient forest, every direction you look is filled by a tree trunk, in such a universe, every direction would be filled with stellar brilliance. The entire night sky, in this model, should be as uniformly bright and searing as the surface of our own sun. Yet when we look up, we see a profound and beautiful darkness punctuated by stars. The reality glaringly contradicts the logical prediction. This is not a minor puzzle. It is a direct observational paradox that forced astronomers to confront a fundamental flaw in their assumptions about the nature of everything. The resolution to this paradox reveals a universe that is neither static nor infinitely old. The first key is the finite speed of light. Light does not travel instantaneously. It takes time, a great deal of time, to cross the vast gulfs between galaxies. Because the universe has a beginning, a starting point we call the Big Bang approximately 13.8 billion years ago, there is a cosmic horizon. We can only see the light that has had sufficient time to travel from its source to our telescopes since the beginning. There are stars and galaxies so immensely far away that their light, even traveling at the ultimate speed limit of the cosmos, simply has not reached us yet. Our observable universe is a finite bubble within a potentially much larger whole, and much of the light from beyond that bubble is still on its way. The second, even more critical piece is the expansion of space itself. The universe is not static, it is stretching, causing the distances between galaxies to increase over time. This expansion has a direct and observable effect on the light traveling through it. As light waves journey across an expanding cosmos, the space they are traveling through stretches, which in turn stretches the light waves themselves. This process, called cosmological redshift, shifts the light toward longer, redder wavelengths. For visible light, this shift means the light becomes dimmer and redder, draining its energy. For the most distant galaxies, their light is redshifted so dramatically it falls completely out of the visible spectrum and into the infrared or even radio bands. Their brilliant starlight is in effect diluted and transformed into a form our eyes cannot see. The combined effect of a finite age and an expanding space solves the paradox. The sky is dark because the universe has a history, a beginning, and a dynamic nature. Many of the stars whose light should fill the void have not had time to reach us, and the light from the most ancient, distant sources has been stretched into near nothingness by the relentless expansion of everything. Olbers' simple question about a dark night sky became one of the strongest early arguments against an eternal, unchanging universe. It helped steer cosmology away from a static model and toward the dynamic, evolving picture we have today. It demonstrates with elegant clarity how a basic observation, something anyone can witness from their own backyard, can challenge our most foundational assumptions about reality. The darkness above is not an empty void. It is a historical record, a testament to a cosmos with a birthday, one that is still growing and changing. Its earliest stories, written in the fading whispers of light, we are only now beginning to decode. Shakespeare's genius echoes through the centuries, but what if it was not his own? A different kind of time travel paradox emerges, one not of physical impossibility but of informational origin. This is the Bootstrap Paradox. In this scenario, a time traveler journeys to Elizabethan England and presents William Shakespeare with a beautifully bound, complete collection of his own future plays and sonnets. Shakespeare, astonished, simply copies the works and publishes them under his name, achieving everlasting fame. The plays are written, performed, and remembered throughout history, eventually making their way back to the time traveler, who then takes them back to give to the young bard. The question is devastatingly simple. Who, then, is the true author of Hamlet? The information, the plays themselves, have no point of creation. They were never originally composed by any mind. They simply exist trapped in an endless, closed loop with no discernible beginning. The books are not copied from an original. They are the original, a perfect circle of causality where the effect is also the cause. This paradox strips away the comfort of linear history. It challenges the very foundation of creation and intellectual property, suggesting that in a universe with closed timelines, ideas could be self-created, appearing from nowhere, belonging to no one. For physicists, this is not just a literary curiosity. It becomes a serious consideration in models of the universe that permit closed time-like curves, theoretical pathways through warped spacetime that loop back on themselves. Could a particle or a book or a piece of information be its own ancestor? The Bootstrap Paradox pushes our understanding of cause and effect to the brink, forcing us to ask whether the universe's laws inherently forbid such loops to prevent logical chaos, or if they are a strange but permissible feature of reality's deepest geometry. It suggests that in some corner of a possible cosmos, every great idea, every invention, every symphony might not have a creator, but only a perpetual curator in an infinite loop of existence. But if information is truly indestructible, then black holes present the ultimate cosmic shredder. According to the bedrock principles of quantum mechanics, information is sacred. The quantum state of every particle, the precise arrangement of every atom that makes up a book or a star, is never truly lost. It may be scrambled, transformed, or dispersed into an incredibly complex pattern, but in principle it could always be recovered. This principle of unitarity is a non-negotiable rule for how quantum systems evolve. Yet, for decades, black holes seem to offer a glaring exception. When anything crosses the event horizon, the point of no return, it is lost to our universe forever according to Einstein's general relativity. The matter is crushed into the singularity, and all the intricate information about what fell in, whether it was a cloud of hydrogen or the complete works of Shakespeare, seems irretrievably erased. This conflict deepened with Stephen Hawking's revolutionary discovery. He showed that black holes are not perfectly black. Due to quantum effects at their very edge, they slowly leak a faint glow of particles, now called Hawking radiation. Over eons, this process causes the black hole to lose mass and eventually evaporate completely, disappearing in a final flash. Hawking initially concluded that this radiation was purely thermal, a featureless hiss carrying no information about what had fallen in. If the black hole vanishes and only random heat remains, then the information about everything it ever consumed is permanently lost to the cosmos. This is the black hole information paradox, a direct and violent clash between the two great pillars of physics. Quantum mechanics demands information preservation, while Hawking's calculations suggested black holes violate this law. The paradox suggests our understanding of reality is incomplete at the most extreme frontier. One of the most profound potential resolutions comes from the holographic principle. It proposes a staggering idea. All the information describing everything within a volume of space can be perfectly encoded on the two-dimensional surface that bounds it, like a cosmic hologram. For a black hole, this means the information of every object that falls in is not destroyed at the singularity. Instead, it is imprinted in a scrambled, quantum form on the event horizon itself, the black hole's spherical surface. As the black hole evaporates via Hawking radiation, this encoded information is slowly and chaotically released back into the universe through the radiation's subtle correlations. The information was never inside the black hole in the way we thought. It was always painted on its skin. Another possibility is that black holes do not completely evaporate. They might leave behind a tiny, stable remnant, a fossil containing all the compressed information of its past. Yet this idea brings its own dizzying challenges, suggesting an almost infinite number of such remnants could eventually populate the universe. Solving this paradox is not an academic exercise. It is widely seen as the essential stepping stone to a theory of quantum gravity, a framework that would finally unite the laws of the very large with the laws of the very small. The fate of information falling into a black hole is a proxy war for the fate of causality and determinism in our universe. It asks whether the cosmos keeps perfect records, or if some doors, once closed, are sealed forever. A tiny, intelligent gatekeeper could, in theory, unravel the universe's relentless slide toward disorder. This is the paradox of Maxwell's demon, a thought experiment conceived by the physicist James Clerk Maxwell in 1867. He imagined a minuscule, clever being stationed at a trapdoor in a wall separating two chambers filled with gas. Both chambers start at the same temperature, meaning the molecules inside are bouncing around with a similar average speed. The demon's task is simple, yet its implications are revolutionary. It watches the molecules approach the door. When it sees a particularly fast-moving molecule coming from the right chamber, it opens the door just long enough to let it pass into the left. When a slow-moving molecule approaches from the left, it lets that one slip into the right. It slams the door shut for all other molecules. Over time, this selective sorting would have a dramatic effect. The left chamber would fill with fast, hot molecules, heating it up, while the right chamber would be left with only the slow, cold ones cooling it down. A temperature difference would be created out of uniform chaos, all without the demon apparently doing any physical work like pushing a piston or turning a wheel. This is the heart of the paradox. The second law of thermodynamics is one of the most non-negotiable rules in all of science. It states that the total entropy or disorder of an isolated system can never decrease over time. It is the reason heat flows from hot to cold, never the other way, and why perpetual motion machines are impossible. Maxwell's demon, by sorting the molecules, seems to be decreasing the entropy of the two-chamber system, creating order from randomness and violating this fundamental law. For over a century, this clever scenario haunted physicists. How could a law as absolute as the second law be broken by a mere thought experiment? The brilliant resolution did not come from questioning thermodynamics, but from expanding it to include a new, fundamental currency of the universe, information. The demon's secret flaw is that it is not a passive observer. To do its job, it must first acquire information. It must measure the speed and position of each approaching molecule to decide whether to open the door. In the late 20th century, physicists like Rolf Landauer and Charles Bennett showed that this process has a hidden, unavoidable cost. The demon, whether it is a microscopic being or a nanoscale machine, needs a memory to store its measurements like a mental notepad. To make a new decision for the next molecule, it must erase the old information from its notepad to make space. And here lies the critical twist. Landauer's principle established that erasing information is not a free process. It is a physically irreversible act that always dissipates energy as heat, increasing the entropy of the surrounding environment. The entropy decrease inside the chambers is perfectly balanced and in fact surpassed by the entropy increase generated when the demon's memory is cleared. The second law stands triumphant. This revelation was a seismic shift in our understanding. It proved that information is not an abstract concept, it is physical. It has weight in a sense, and it has a real, measurable energy cost. Maxwell's demon, a puzzle about gas molecules, became the foundational link connecting the worlds of thermodynamics, information theory, and the very limits of computation. It tells us that every calculation, every bit of data processed or deleted in the devices we hold in our hands, is ultimately governed by the same universal law that dictates the flow of heat and the arrow of time. Knowledge itself requires an energy toll paid to the universe in the currency of entropy. Einstein himself could not accept the bizarre implications of his own quantum theory. In 1935, he joined with physicists Boris Podolsky and Nathan Rosen to formulate a devastating critique, a thought experiment designed to prove that quantum mechanics was an incomplete description of reality. They focused on the phenomenon of entanglement, where two particles are created together and become linked in a single, shared quantum state. The mathematics showed that if you then separated these particles by any distance, even across the galaxy, measuring a property of one, like its spin, would instantaneously force the other particle into a corresponding state. To Einstein, this was an absurdity he famously called spooky action at a distance. It seemed to imply a signal traveling faster than light, a direct violation of his own theory of relativity, which established the speed of light as the universe's ultimate speed limit. More deeply, it clashed with his philosophical belief in local realism, the idea that objects have definite properties independent of measurement, and that no physical influence can travel faster than light. The EPR paradox, as it became known, was a stark declaration that quantum mechanics must be wrong or, at best, incomplete, missing some hidden variables that predetermine the particle's behavior all along. For decades, this stood as an impassable philosophical divide. Then, in the 1960s, physicist John Bell found a way to translate the argument into a testable mathematical inequality. Bell's theorem showed that if local hidden variables existed, entangled particles would correlate in a certain limited way. But if quantum mechanics was correct, they would exhibit stronger correlations. When experimental technology finally caught up in the 1970s and 80s, the results were unequivocal. The experiments, most definitively by Alain Aspect and his team, violated Bell's inequality. The universe chose spookiness. There was no slower-than-light hidden message, no predetermined agreement. The particles were genuinely connected in a way that transcended classical space. This was not communication in any usable sense, as no information or energy was transmitted, but it was a profound form of correlation that seems to stitch the fabric of reality together with threads that ignored distance. The resolution of the EPR paradox forced a fundamental shift. We had to abandon either locality, the idea that distant events cannot influence each other instantly, or realism, the idea that particles have definite properties before we look. Most interpretations of quantum mechanics sacrifice local realism, accepting that the universe is fundamentally non-local at a quantum level. This astonishing victory for quantum theory is not just a philosophical curiosity. It is the very foundation of the emerging field of quantum information science, enabling technologies like quantum cryptography and quantum computing, which rely on harnessing this spooky connection to perform tasks impossible for any classical machine. Einstein's greatest objection became one of quantum theory's most powerful and validated features, revealing a universe far more deeply interconnected than he ever imagined. The story of Achilles and the tortoise is more than a clever riddle. It is a declaration of war against motion itself. Zeno of Elea, a philosopher of ancient Greece, crafted a series of arguments so sharp they seemed to prove that movement, change, and even plurality were nothing but grand illusions. His most famous paradox sets the legendary swift hero Achilles in a race against a slow-moving tortoise, granting the tortoise a modest head start. By the time Achilles reaches the tortoise's starting point, the tortoise has crawled a little further ahead. By the time Achilles covers that new distance, the tortoise has advanced again, however slightly. Zeno's logic suggests that Achilles must always first reach the point the tortoise just left, forever closing an infinite series of gaps without ever actually catching up. Motion, in this view, becomes an impossible task, a never-ending checklist of smaller and smaller steps that can never be completed. This is the dichotomy paradox applied to a race, and it exposes a deep anxiety about infinity and the nature of physical reality. If a finite distance can be divided into an infinite number of parts, how can anything ever traverse them all? The paradox freezes time into an endless sequence of frozen snapshots, each showing the runner in a new position, but never showing the smooth, continuous flow we experience every day. For over 2,000 years, these puzzles stood as formidable obstacles, highlighting a critical gap between human intuition and mathematical description. The solution did not arrive until the invention of calculus in the 17th century, which provided the language to tame the infinite. The breakthrough was the concept of a limit and the understanding of a convergent infinite series. Mathematicians like Newton and Leibniz showed that an infinite sum of ever-shrinking quantities can add up to a perfectly finite, reachable total. The infinite steps between Achilles and the tortoise are not a barrier but a description. The time it takes to complete each smaller step also shrinks accordingly. and the sum of all these diminishing time intervals converges to a specific, finite moment, the exact instant Achilles overtakes his sluggish competitor. While Zeno's paradoxes do not challenge the laws of modern physics, their legacy is monumental. They forced thinkers to confront the logical foundations of continuity and change, demanding a rigorous framework that could account for motion without contradiction. This philosophical struggle directly paved the way for the mathematical tools that would later become essential for describing everything from the orbit of planets to the flow of electricity. They remind us that the most persistent puzzles, those that seem to trap us in loops of impossible logic, are often the very signposts pointing toward the next great leap in understanding. The smooth motion we take for granted rests upon a foundation built by wrestling with the infinite. Saving for a rainy day is a universal virtue, a principle of personal responsibility. Yet when this sensible individual choice is adopted by an entire society at once, it can trigger a devastating economic collapse. This is the paradox of thrift, a concept from economics that reveals a stunning truth about complex systems. If every household, fearing a downturn, decides to simultaneously cut spending and increase savings, the immediate effect seems prudent. But money saved is money not spent on goods and services. This collective reduction in consumption causes businesses to see falling revenues. They respond by cutting production, laying off workers, and reducing investment. As incomes plummet across the economy, the total capacity for saving actually shrinks. The very act of trying to save more en masse results in a poorer society where, in the end, there is less wealth to save. A rational local decision, when scaled up, produces an irrational and destructive global outcome. This is not merely a financial curiosity. It is a perfect mirror of feedback loops we see throughout the physical world. Consider a sealed ecological environment, like a small lake. Each individual algae cell strives to optimize its own growth, absorbing as much sunlight and nutrients as possible. This is a successful local strategy, but if every algae cell does this simultaneously, the population explodes. The lake becomes choked, sunlight cannot penetrate, oxygen is depleted, and the entire system collapses in a toxic algal bloom. The individual drive for success leads to collective ruin. In thermodynamics, a similar principle emerges. A refrigerator in your kitchen works by pumping heat from its cold interior to your warm kitchen. This is efficient for keeping food fresh, but if you tried to cool your entire house by leaving the refrigerator door open, the system would fight itself. The motor would work relentlessly, dumping more heat into the room than it removes from the interior, actually making the whole space warmer. The appliance, optimized for a local task, becomes counterproductive when its effect is scaled to the global environment. These parallels teach us a profound lesson about emergence and non-linearity. The behavior of a complex system cannot be predicted by simply adding up the behaviors of its individual parts. Simple, logical rules followed locally can intertwine through feedback to create stunningly counterintuitive and often detrimental global consequences. This insight is vital far beyond economics or ecology. It helps us understand the daunting challenge of climate systems, where billions of individual decisions about energy use combine into planetary scale shifts. It even offers a lens for galactic evolution, where the local collapse of stars into black holes can regulate the formation of new stars across an entire galaxy. The universe, it seems, is filled with systems where the whole is not just greater than the sum of its parts, but often behaves in ways the parts would never suggest. The paradox of thrift reminds us that in an interconnected reality, no action is ever truly isolated, and the path to collective well-being often requires navigating a landscape where individual logic and global logic can point in opposite directions. A green apple sitting on a kitchen counter seems utterly irrelevant to the color of ravens. Yet, within the strange logic of confirmation, it quietly whispers support for the claim that all ravens are black. This is the Raven Paradox, a puzzle that dissects the very engine of scientific discovery, inductive reasoning. We observe specific instances to support a general law. Every black raven we see strengthens our belief in the statement all ravens are black. The paradox emerges from a simple logical rewrite. The statement all ravens are black is logically equivalent to saying all non-black things are non-ravens. They are two sides of the same coin. Therefore, anything that confirms the second statement should also confirm the first. Now, look at that green apple. It is a non-black thing, and it is also a non-raven. It perfectly fits the category of all non-black things are non-ravens. By strict logic, finding a green apple should provide a tiny bit of evidence that all ravens are black. This feels instinctively wrong, even absurd. How can data from an entirely different domain, the color of fruit, tell us anything about the plumage of birds? The paradox does not claim this is how science is done, but it ruthlessly exposes a vulnerability in how we think evidence works. It challenges the notion of what counts as relevant confirmation. If we accept the logical equivalence, then searching for white shoes, blue cars, or yellow flowers in your backyard becomes a valid, if spectacularly inefficient, method for ornithology. This absurdity forces a deeper conversation about the context of inquiry. In real science, we do not test the law all ravens are black by examining everything that is not a black raven. We focus our investigation on the relevant class, the ravens themselves. The paradox highlights that evidence is not just about logical form. It is about the framework of our investigation, our prior knowledge, and what we consider a meaningful test. This connects directly to a profound challenge in physics known as underdetermination. It is the unsettling idea that for any given set of observational data, there could be multiple, even wildly different, scientific theories that explain it equally well. Our telescopes collect light from distant galaxies, and our particle colliders record sprays of exotic debris. These are our green apples and our black ravens, our limited local observations. From this finite data, we must infer universal laws governing the entire cosmos or the fundamental constituents of matter. The Raven Paradox reminds us that our evidence is always incomplete. We can never observe all ravens everywhere for all time. We can never recreate every possible condition in the universe. Therefore, our most cherished theories, from the nature of dark matter to the existence of extra dimensions, are always to some degree underdetermined by the data. This is not a flaw, but a fundamental condition of knowledge. It forces humility into the scientific process, a constant awareness that new evidence from a surprising place, perhaps as seemingly unrelated as a green apple, could one day force us to rewrite our most fundamental maps of reality. The paradox ultimately asks us to consider the philosophical bedrock beneath our magnificent edifice of physics. What makes one piece of evidence strong and another trivial? How do we choose between competing theories that both fit the facts? The search for answers to these questions is what keeps science from being a mere catalogue of observations and transforms it into a relentless, self-correcting journey toward a deeper, though perhaps never final, truth. Our very identity, the sense of a continuous self, faces a similar erosion in the face of constant renewal. The ancient Greeks posed a riddle about a legendary ship preserved in a harbor as a monument. Over the centuries, as its wooden planks rotted, each one was carefully removed and replaced with an identical new plank. Eventually, not a single original piece of the vessel remained. The philosophical question is deceptively simple. Is the ship in the harbor still the Ship of Theseus? If not, at what precise moment did it cease to be itself? Was it after the first plank was swapped, or the 50th, or the very last? This is not a question about carpentry, but about the nature of objects and persistence through time. We intuitively cling to the idea that an object's identity is tied to the specific atoms that compose it, yet our own bodies silently refute this notion. The cells that make up your skin, your blood, even the neurons in your brain, are in a constant state of turnover, replaced by new cells over cycles of years. The person you were a decade ago was, on a physical level, composed of almost entirely different matter, and yet you feel a profound and unbroken continuity of self. This paradox forces us to ask what truly constitutes a thing. Is it the raw material, or is it something more abstract like the pattern, the structure, or the information that material embodies? Physics offers startling parallels that push this idea to the fundamental level. Consider a candle flame. It appears as a single, persistent entity, a dancing form of light and heat. But look closer. The flame is not a static object. It is a dynamic process, a region of space where chemical reactions occur. The molecules that make up the flame at this very second are completely different from those that composed it a second ago. They are consumed, transformed, and replaced by a constant flow of new fuel and oxygen. The flame's identity is not in its matter, but in the ongoing process itself, the stable pattern of energy release. This is a direct echo in thermodynamics, where we describe systems like a whirlpool in a river or even a living organism. Their defining properties, their temperature, their shape, their function persist despite the ceaseless exchange and flow of their constituent particles. The most profound extension of this idea comes from quantum field theory, our best description of the subatomic world. In this framework, what we call fundamental particles, like electrons or quarks, are not tiny, indestructible billiard balls. They are better understood as localized excitations, like temporary knots or ripples in an all-pervading, invisible quantum field. An electron in your hand and an electron in a distant star are not separate, permanent little things. They are identical manifestations of the same underlying electron field. Their identity comes from their shared properties, their mass, their charge, their spin, which are dictated by the field itself, not from being a unique speck of stuff. This perspective dismantles the classical notion of objects as discrete, permanent entities. It suggests that at the most basic level, reality is not a collection of things, but a symphony of interacting fields and persistent processes. The Ship of Theseus, then, transforms from a quaint puzzle into a deep probe of physical reality. It challenges us to see identity not as a property of matter, but as a property of information, organization, and function. The ship is the same because the pattern of planks, the design, the history, and the purpose remain coherently intact. In the same way, a river remains the same river despite the constant flow of new water, and you remain you through the relentless renewal of your cells because the pattern of your memories, your personality, and your life's narrative holds steady. This shift in perspective is crucial for grappling with the true nature of fundamental particles, where permanence is an illusion, and existence is a dance of transient excitations on the eternal stage of quantum fields. A judge's sentence becomes a trap for the mind as much as the body. The prisoner is told they will be hanged at noon on some weekday of the following week, but with one cruel, logical twist, the hanging will be a surprise. It will occur on a day when the prisoner does not expect it. Standing in their cell, the prisoner begins to reason. They cannot be hanged on Friday, they conclude. If I am alive by Thursday evening, they think, then the hanging must be on Friday. But if I know it must be on Friday, then it would not be a surprise. Therefore, Friday is eliminated. With Friday gone, they apply the same logic to Thursday. By Wednesday night, if I am still alive, the hanging must be on Thursday. But then I would expect it, so Thursday is also impossible. One by one, they eliminate every day of the week, concluding that the surprise hanging cannot happen at all. Confident in their flawless logic, they are then completely astonished when the guards arrive on Wednesday, a day they had ruled out. the sentence is carried out as a total surprise. This is the unexpected hanging paradox, a dizzying loop where reasoning about your own future knowledge seems to invalidate the future itself. The prisoner's logic appears impeccable, yet it leads to a conclusion that is starkly contradicted by reality. The paradox exposes the treacherous ground of self-referential prediction, where thinking about what you will know later changes the landscape of what is possible now. It is not a puzzle about capital punishment, but a profound exploration of the limits of knowledge and the strange ways expectation shapes our perceived reality. In the world of physics, this self-referential knot finds a powerful echo in the mysterious process of quantum measurement. Imagine a quantum system, like a particle that can spin in two directions. According to the theory, until it is observed, the particle does not have a definite spin. It exists in a superposition, a blend of both possibilities. The moment a physicist sets up a detector to measure the spin, the system is forced to choose a single, definite state. The act of measurement, the act of asking the question, seems to collapse the cloud of possibilities into one concrete answer. This is eerily reminiscent of the prisoner's reasoning. The prisoner's analysis of the future days was, in a sense, a form of measurement, a logical attempt to pin down a definite day for the hanging. But that very act of prediction changed the conditions of the problem, eliminating days and making the final outcome a surprise. In quantum mechanics, we cannot talk about a particle's properties as existing independently of the measurement we choose to make. The observer is entangled with the outcome. The unexpected hanging paradox in its own logical domain highlights this blurry line. When does knowledge about a future event actually crystallize? Is it when the event is logically deduced or only when it physically occurs? The prisoner thought their deduction gave them certainty, but it only gave them a false confidence that altered their expectations. This paradox ultimately challenges our classical intuition about how knowledge works. We like to believe that the world exists in a definite state, and we simply discover facts about it. But both this logical riddle and quantum theory suggest something more interactive. Our predictions, our models, and our very methods of inquiry can become part of the system we are studying, influencing what we find. It is a reminder that in probabilistic systems, whether a courtroom riddle or a quantum experiment, the boundary between the knower and the known is not always clear. The universe may not simply reveal its secrets to a passive observer, but may instead respond to the questions we think to ask, delivering answers that can still, against all our sophisticated reasoning, manage to surprise us. Mathematics can conjure a perfect duplication from a single sphere, a feat that seems to mock the very idea of conservation. This is the Banach-Tarski Paradox, a theorem so bizarre it feels like a magician's trick played on reality itself. The claim is astonishingly simple to state and impossible to visualize. Take a solid ball like a billiard ball. The theorem proves that this ball can be mathematically dissected into a finite number of pieces. These pieces are then rearranged, using only rotations and translations, without stretching or deforming them, to create two new balls. Each of these two new balls is perfectly identical in size and shape to the original single ball. One becomes two, with nothing added and nothing taken away from the total substance. This appears to be a blatant violation of a fundamental law we hold sacred in the physical world, the conservation of mass and volume. You cannot take a lump of clay, cut it into pieces, and reassemble those pieces into two lumps of clay, each the same size as the first, not without adding more clay. Yet the Banach-Tarski theorem states that in the pure, abstract realm of mathematical sets, you can do exactly that. The resolution to this apparent impossibility lies in the nature of the pieces themselves. The dissection does not produce chunks you could ever hold in your hand. The pieces are not smooth, solid fragments. They are what mathematicians call non-measurable sets, collections of points so infinitely complex, jagged, and scattered that they defy any sensible notion of volume. They are fractal dust of such intricate structure that they cannot be assigned a meaningful size. Because these pieces have no well-defined volume to begin with, the concept of conserving volume simply does not apply to them. The magic trick works because the starting materials, the pieces, are mathematical phantoms that could never exist as physical objects. This profound result is not a flaw in mathematics, but a direct consequence of a powerful tool known as the axiom of choice. This axiom allows mathematicians to, in a sense, reach into an infinite set and select an element from it, even when there is no specific rule for making that choice. It is an assumption that feels intuitively reasonable for working with infinities, but it leads to startling consequences, like the creation of these non-measurable monsters. The Banach-Tarski Paradox is therefore not a paradox of physics. It is a paradox of intuition, a dazzling demonstration that the logical world of abstract mathematics can follow rules that have no counterpart in our tangible universe. It serves as a crucial cautionary tale for theoretical physics. When we build models of reality using powerful mathematical tools, especially those involving infinity and abstract choice, we must be vigilant. The equations might permit a solution that is mathematically impeccable, like duplicating a sphere, but physically nonsensical. It reminds us that the map is not the territory. The elegant, sometimes shocking landscapes of pure mathematics are a language for describing reality, but they are not reality itself. The theorem stands as a monument to the creative power of the human mind, capable of conceiving shapes and operations that the physical cosmos could never embody, teaching us that the boundary between the possible and the impossible is often drawn not by logic alone, but by the stubborn, concrete nature of the world we inhabit. A universe of perfect, endless stillness should already be our reality. The laws of thermodynamics are unequivocal. Entropy, a measure of disorder, always increases in any isolated system. This relentless march points toward an inevitable final state for our cosmos, the heat death. In this distant future, all energy will be evenly distributed. Every corner of space will share the same infinitesimal temperature, and no gradient will remain to power stars, planets, or thought. It is the ultimate equilibrium, a silent, eternal twilight where nothing ever happens again. Yet here we are, in a vibrant universe of swirling galaxies and shining stars, a place clearly far from that uniform graveyard. This presents a staggering temporal paradox. If the universe is eternal, if it has already existed for an infinite amount of time, then there has been more than enough opportunity for entropy to maximize. The heat death should have occurred an eternity ago. Why hasn't it? The mere fact that we exist to ask the question seems to contradict the very laws that govern our existence. This paradox delivers a devastating blow to any model of a static, unchanging, and eternal cosmos. It tells us the universe cannot have been forever as it is now. Something must have been different in the past, something that set the cosmic clock ticking and gave time its unmistakable arrow. The prevailing answer, supported by overwhelming evidence, is the Big Bang cosmology. Our universe is not eternal in a steady state. It had a beginning, a moment of immense density and temperature approximately 13.8 billion years ago. More importantly, it began in a state of extraordinarily low entropy. Think of it as a pristine, perfectly ordered spring wound tightly at the dawn of time. Everything since has been the slow, irreversible unwinding of that spring. The expansion of space itself provides the ever-growing arena into which entropy can increase, driving the formation of structure, from galaxies to life itself, as the universe journeys from its ordered beginning toward its disordered end. This resolves the timing of the heat death, but it replaces one paradox with a mystery of even greater profundity. Why did the universe start in such a special, low entropy condition? What set that initial spring? This is known as the past hypothesis, and it stands as one of the deepest puzzles in all of physics. It forces us to confront the origin of time's arrow itself. The laws of physics at their most fundamental level are almost entirely time-symmetric. They work just as well running forward or backward. Yet our experience is brutally one-directional. Eggs scramble but never unscramble. Memories are of the past, never the future. This asymmetry, the arrow of time, emerges not from the laws themselves, but from that singular, low-entropy starting point. Our entire experience of cause and effect, of history and memory, may be a cosmic accident, a rare fluctuation in a much larger multiverse, or a clue to a physics before the Big Bang. The heat-death paradox, therefore, is far more than a question about a distant future. It is a piercing inquiry into the first moment of existence, asking why there was ever a past to remember and why there is still a future yet to unfold. An unstable particle on the verge of decay can be frozen in time simply by watching it. This is the quantum Zeno effect, a phenomenon where the relentless gaze of measurement forces a quantum system to remain unchanged. It is named for the ancient philosopher whose paradoxes questioned motion, but here the stakes are far higher, challenging the very nature of change and observation. In the quantum world, an unstable particle, like a radioactive atom, does not have a predetermined moment of decay. Instead, it exists in a superposition, a blend of the possibility of being intact and the possibility of having already decayed. Its wave function, the mathematical description of its state, evolves smoothly over time, increasing the probability of decay as time passes. However, a measurement is not a gentle peak. It is a violent interrogation that forces the particle to pick a state, to collapse its wave function into a single, definite answer. Now, if you measure the particle almost immediately after it is prepared, you are overwhelmingly likely to find it still intact. The crucial twist is that this act of measurement resets the clock. The wave function collapses back to the starting point, the undecayed state, and the probabilistic evolution toward decay begins all over again. By repeating this measurement process rapidly and continuously, you can, in effect, reset the system again and again before it has any significant chance to decay. The particle is trapped by observation, like a watched pot that never boils, not because of superstition, but because of the fundamental rules of quantum reality. This is not just a theoretical curiosity. It has been demonstrated in laboratories using lasers to repeatedly measure the state of atoms, preventing them from making a quantum jump to a different energy level. The effect blurs the line between observer and observed beyond any philosophical debate. It shows that in the quantum realm, to look is not to passively receive information. It is to actively intervene, to reach into the system and mold its fate. This has profound implications for the technology of tomorrow, particularly in the race to build quantum computers. The heart of such a machine is the qubit, a delicate quantum bit that exists in a superposition. The greatest enemy of a qubit is decoherence, the process by which it loses its quantum magic by interacting with its environment, which acts as an unintentional measurement. The quantum Zeno effect suggests a radical defense strategy. By carefully and strategically measuring the qubit, not to read its value but to nudge it, we could potentially stabilize it, locking it into its desired state and protecting its fragile superposition from the disruptive noise of the outside world. This paradox transforms observation from a simple act of knowing into a tool of creation and preservation, revealing a universe where reality is not just seen, but solidified by the questions we choose to ask. 3 dimensions feel as natural and absolute as breathing. We move left and right, forward and back, up and down. This trio of spatial directions is the stage upon which every event in our lives unfolds, from the flight of a ball to the orbit of a planet. Physics reveals this number is not arbitrary. In a universe with only two dimensions, gravitational orbits as we know them become unstable and complex. Intertwining biological systems like a digestive tract would be impossible. In 4 or more spatial dimensions, the forces that bind atoms together weaken dramatically, likely preventing the formation of stable matter. 3 appears to be the magic number, the sweet spot where physics allows for the rich complexity that leads to stars, planets, and observers like us. Yet this comfortable fact hides a profound contradiction. Our most ambitious attempt at a theory of everything, string theory, paints a radically different picture. To make its equations work, to unify all forces and particles, string theory requires not 3, but 10 or even 11 dimensions. Where then are the extra 7 or 8? The proposed answer is compactification. Imagine a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line. But an ant crawling on its surface experiences a second dimension, the tiny circular path around the hose's circumference. In string theory, the extra dimensions are theorized to be curled up on themselves at an inconceivably tiny scale, a billion times smaller than an atom, at every single point in our familiar three-dimensional space. We are like the distant observer, blind to the intricate miniature loops that may define the fundamental fabric of reality. This is the Dimensionality Paradox. Why do we experience exactly 3 expansive classical dimensions, while the underlying mathematics suggests a far richer geometric landscape? One compelling line of reasoning is anthropic. It suggests that stable, long-lived universes capable of supporting complex chemistry and conscious observers may only arise in configurations with exactly 3 large spatial dimensions. In a hypothetical multiverse, where different cosmic bubbles have different numbers of expanded dimensions, we inevitably find ourselves in one of the rare bubbles where the conditions are just right for our existence. The number 3, then, might not be a fundamental law written in stone, but a local byproduct of our cosmic address, an emergent property of our particular pocket of reality. This challenges us to rethink the nature of constants themselves. Could the dimensionality of space be a frozen accident from the universe's first moments, a symmetry that broke in a specific way as the cosmos cooled? If so, other domains of reality, forever beyond our reach, could boast 4, 5, or even more dimensions of macroscopic freedom, hosting forms of matter and life we cannot begin to conceive. Our three-dimensional perception becomes not the full story, but a single, flat page torn from a vast, multidimensional library. The solidity of the world around us, the very space we navigate, may be just one slice of a deeper, hidden geometry, a constant reminder that the stage itself holds secrets far stranger than any play performed upon it. Our reality could be a convincing illusion running on a cosmic computer. This is the simulation paradox, a modern argument that uses simple statistics to question the very nature of existence. The reasoning begins with a projection about technological advancement. If a civilization survives long enough to reach a post-human stage, it would likely possess computing power beyond our imagination. One potential use of such power would be to run detailed, conscious simulations of entire universes, populated by simulated beings with their own rich inner lives. Now, if even a small fraction of such advanced civilizations chose to run many such simulations, the total number of simulated minds would quickly dwarf the number of original, biological minds in the base reality. From a purely statistical standpoint, if you are a conscious being, you are far more likely to be one of the countless simulations than one of the rare originals. Therefore, it is more probable that we are living in a simulation right now than in the fundamental, physical universe. This argument, formalized by philosopher Nick Bostrom, does not claim we are definitely in a simulation. It presents a trilemma, suggesting one of 3 propositions must be true. Either civilizations like ours almost always go extinct before reaching a simulation-capable stage, or advanced civilizations almost never choose to run such simulations, or we are almost certainly living in one. The first option is a sobering answer to the Fermi Paradox. The second requires a universal ethical or practical constraint we cannot foresee. And the third is the startling conclusion that reshapes our cosmic identity. While this is a philosophical and statistical argument rather than a strict physics paradox, its implications ripple directly into foundational science. It invites us to look at the oddities of our universe through a new lens. Could the strange, probabilistic rules of quantum mechanics, where particles lack definite properties until observed, be a clever programming shortcut? In a vast simulation, rendering the precise state of every subatomic particle in real time would be computationally prohibitive. It would be far more efficient to only calculate definite properties when something or someone is looking, a process eerily similar to the quantum measurement collapse. Similarly, the idea that spacetime itself might be discrete, composed of tiny, indivisible units like pixels on a screen, aligns with how a simulation would manage its fundamental resources. These are not proofs but haunting resonances. The simulation hypothesis ultimately forces a profound philosophical shift. What evidence could ever convince us we are in base reality? Any experiment we design, any law of physics we uncover, could simply be part of the simulation's consistent internal code. The search for glitches in the matrix, like anomalies in high-energy particle collisions or odd statistical distributions in cosmic constants, becomes a new kind of experimental frontier. This paradox challenges us to define what we mean by real. Is reality defined by its material substance, or by the consistency of experience and the logical structure of its laws? It turns our gaze inward, suggesting that the most fundamental mystery may not lie in the distant cosmos or the quantum void, but in the nature of our own conscious perception, and the unsettling possibility that the universe we strive to understand is a masterpiece not of nature but of artful engineering. Galaxies spin with a speed that should tear them apart. At their outer edges, stars whip around the galactic center so swiftly that the combined gravity of all the visible stars, gas, and dust is simply not enough to hold them in orbit. According to the laws of gravity, these fast-moving stars should be flung into the void, scattering galaxies across the cosmos. Yet they remain bound, tracing their luminous paths as if gripped by an invisible hand. This mismatch, revealed by galactic rotation curves, is one of the most robust observations in modern astronomy. It demands the presence of something unseen, a vast reservoir of mass that does not emit, absorb, or reflect light, something we call dark matter. The evidence for its gravitational influence is overwhelming, sculpting the large-scale structure of the universe and bending the light from distant galaxies. We can map its shadowy contours across the heavens, but here lies the profound paradox. Despite knowing where it is and what it does, we have never directly caught a single dark matter particle. Our most sensitive detectors, buried deep underground to shield from cosmic noise, have remained silent. Our particle colliders, smashing matter together at nearly the speed of light, have produced no unambiguous signal. We are in the strange position of studying the footprint of a creature we have never seen, building an entire cosmology around a ghost. This glaring discrepancy between undeniable gravitational effects and the complete absence of a direct detection forms one of the most urgent puzzles in physics. It forces a fundamental question upon us: is the problem with the hunter or with the nature of the prey? One possibility is that our search is misguided because dark matter is not a simple, lone particle waiting to bump into our detectors. It could be an entire hidden sector, a complex dark universe with its own families of particles and forces, interacting with our familiar matter only through the faint whisper of gravity. Perhaps dark matter particles are simply too massive for our current colliders to create, or too weakly interacting for our underground experiments to sense, passing through our planet as if it were empty space. A more radical solution challenges not the missing matter, but the law of gravity itself. The theory of modified Newtonian dynamics, or MOND, proposes that on the vast, diffuse scales of galactic outskirts, gravity behaves differently than Newton or Einstein predicted. It suggests a slight tweak to the equations, one that explains the rapid rotation of stars without invoking any unseen substance. In this view, there is no paradox because there is nothing to detect, only a deeper law of gravity waiting to be understood. Yet MOND faces its own severe challenges, struggling to explain all the gravitational effects observed in colliding galaxy clusters, where dark matter's influence seems to separate clearly from the visible matter. The dark matter paradox, therefore, is not a single mystery but a fork in the road of cosmic understanding. One path leads us to a universe filled with exotic, unknown particles that form the hidden skeleton of everything we see. The other path leads to a revision of our most trusted theory of gravity, a pillar of physics for over a century. Both possibilities are revolutionary. This puzzle lies at the very heart of modern astrophysics, for the nature of dark matter dictates the ultimate fate and structure of the cosmos. It holds the blueprint for how galaxies form and how they will evolve over billions of years. The silence of our detectors is not an emptiness, but a loud and persistent question mark hanging over our model of reality, a reminder that the universe may be keeping its greatest secret hidden in plain sight, woven into the very fabric of the darkness between the stars. Empty space is not truly empty. According to quantum field theory, the vacuum is a seething sea of temporary particles and fields, constantly flickering in and out of existence. These quantum fluctuations grant the vacuum an intrinsic energy, a background hum to the cosmos. When physicists calculate the predicted density of this vacuum energy, the result is a number of such staggering magnitude it defies comprehension. It suggests that empty space should possess an energy density around 1 followed by 120 zeros greater than what we actually observe. This is not a small discrepancy. It is the single worst mismatch between theory and observation in the entire history of science, a numerical chasm so vast it has been called the Vacuum Catastrophe. It means our two most successful theories, quantum mechanics and general relativity, are not just in tension, they are screaming contradictory truths about the very fabric of nothingness. One predicts a vacuum so energetic it would have ripped the universe apart in an instant, while the other observes a cosmos expanding at a gentle, accelerating pace driven by a faint something we call dark energy. This paradox forces a brutal realization. Either our understanding of the quantum vacuum is fundamentally wrong, or there exists a miraculous cancellation mechanism of unimaginable precision hiding within the math. One hopeful candidate is supersymmetry, a theoretical framework that pairs every known particle with a superpartner. If these superpartners existed, their contributions to the vacuum energy could perfectly cancel out the enormous quantum prediction, leaving behind the tiny residue we see as dark energy. Yet, despite decades of searching, no evidence for these particles has been found. The alternative is even more radical. It suggests we must abandon our classical notion of the vacuum altogether. Perhaps the vacuum energy is not a static number, but a dynamic quantity that has evolved over the lifetime of the cosmos. Or maybe gravity simply does not respond to vacuum energy the way our current equations suggest. This catastrophe is not an obscure technical failure. It lies at the very heart of the universe's expansion and its ultimate fate. The delicate value of dark energy, this faint pressure in the void, is why galaxies can form and life can emerge. If the vacuum energy were even slightly larger, as the raw quantum calculation insists it should be, the repulsive force would have been so powerful that matter could never have clumped together into stars and planets. The cosmos would have been a featureless, accelerating blur, devoid of structure and observers. The vacuum catastrophe, therefore, is the ultimate fine-tuning problem. It asks why the energy of nothing is so exquisitely balanced to allow for something, for everything we see. It is a paradox that whispers our current laws are a shadow on the wall, and that the true nature of emptiness may be the deepest mystery of all. The most likely conscious observer in an eternal cosmos might be a ghost, not a supernatural specter, but a fleeting, self-contained mind, a disembodied brain that spontaneously assembles from the random jostling of particles in the ultimate void. This is the Boltzmann brain paradox, a thought experiment that turns the logic of probability against our entire cosmic experience. It begins with a principle from statistical mechanics, that in a system left to its own devices for an unimaginably long time, every possible arrangement of particles, no matter how unlikely, will eventually occur by random fluctuation. In a truly eternal and infinite universe, the sheer span of time makes the improbable not just possible, but inevitable. The paradox emerges when we compare two wildly different possibilities. On one hand, you have the spontaneous, random formation of a single, fully self-aware brain, complete with false memories of a past and a coherent present moment. On the other, you have the gradual, structured evolution of an entire 14 billion-year-old universe, with its galaxies, planets, and billions of interconnected, biologically evolved conscious beings. From a raw statistical standpoint, the random assembly of one isolated brain is astronomically more probable than the emergence of our vast, ordered cosmos. It requires far fewer particles to fall into an incredibly specific, complex pattern for a fleeting instant. So why then are we not one of these momentary, solipsistic minds, hallucinating a universe that does not actually exist? Why do we instead find ourselves embedded in a coherent, shared reality with a deep, consistent history written in starlight and fossil records? This is not a question about neuroscience, but a devastating critique of certain cosmological models, particularly those that posit an eternal or endlessly cyclic universe. If the cosmos has truly existed forever, then there has been infinite time for these random fluctuations to happen. In such a landscape, Boltzmann brains would outnumber evolved, biological observers like us by an infinite ratio. Our existence as part of a long, structured cosmic story would be an extreme statistical anomaly. The paradox forces cosmologists to confront the initial conditions of our universe with new urgency. The prevailing Big Bang model, with its definite beginning in a low entropy state, offers a kind of escape. It provides a starting gun, a finite history that limits the time available for random fluctuations, making our ordered reality the expected outcome rather than the freak exception. The paradox also sharpens the discussion around the multiverse. If our universe is one bubble in a vast, eternal multiverse, most bubbles might be empty, chaotic voids where Boltzmann brains briefly flicker in and out of existence. We, by necessity, find ourselves in one of the rare, stable bubbles where physics allows for lasting structure and genuine history, because those are the only places where beings capable of asking such a question can arise. This dizzying idea ultimately reframes our search for meaning. It suggests that the very coherence of our memories, the consistency of the laws of physics, and the shared nature of our observed history are not trivial facts but profound cosmic data points. They are evidence against a formless eternity and clues pointing to a universe with a specific, ordered beginning. The Boltzmann brain paradox asks us to trust not just our senses, but the interconnected narrative of reality itself, for in a cosmos where isolated illusion is the norm, our collective, consistent experience is the greatest mystery of all. The fundamental laws of physics hold a secret about time. They are, for the most part, perfectly symmetrical, working just as well if you ran the film of the universe backward. A planet orbiting a star, a photon reflecting off a mirror, even the intricate dance of particles in a collider, all follow equations that do not care about past or future. Yet our lived reality is brutally one-directional. We remember yesterday, not tomorrow. A shattered glass does not reassemble itself. We grow older, never younger. This glaring contradiction is the arrow of time paradox. Why does our universe possess such a definite direction when its underlying rules seem so indifferent to it? The answer appears to lie not in the laws themselves, but in the specific story of our cosmos. The prevailing explanation points to a single, monumental fact: the universe began in a state of extraordinarily low entropy. Think of entropy as a measure of disorder, of how mixed up things are. A pristine egg with its yolk neatly centered in the white has low entropy. A scrambled egg has high entropy. The second law of thermodynamics dictates that in any isolated system, entropy always increases, which is why scrambling is easy and unscrambling is impossible. Our entire observable universe is that isolated system, and it started with its spring wound incredibly tight, in a state of exquisite, improbable order. Everything that has happened since, from the formation of galaxies to the lighting of a match, is part of the long, irreversible unwinding of that spring. The expansion of space provides the ever larger arena into which entropy can grow, creating pockets of local order, like stars and planets and life, even as the overall disorder of the cosmos increases. This explains the arrow we experience. The reason we remember the past is because the past had lower entropy, and our brains are physical structures whose memories are formed by irreversible processes aligned with that universal increase. Causality itself, the idea that causes precede effects, is woven from this fabric, but this brilliant explanation simply pushes the mystery one step further back. Why did the universe begin in such a special, low-entropy condition? This is known as the past hypothesis, and it remains one of cosmology's deepest, most profound puzzles. There is no known law of physics that demands such a starting point. In fact, from a statistical perspective, a high-entropy, disordered beginning is vastly more likely. So why did we get the unlikely one? Some physicists suggest this points to a reality far larger than our own observable bubble. Perhaps our universe is one region within a vast multiverse, and we simply find ourselves in the rare pocket where the initial conditions were just right for the emergence of complexity and observers. In this view, the arrow of time is not a fundamental feature of reality, but a local accident of our cosmic address. Others seek answers in a physics before the Big Bang, in cyclical models or theories of quantum gravity that might explain how such a low-entropy state could naturally arise. This perspective is profoundly humbling. It suggests that the flow of time, the very foundation of our conscious experience, of history and memory and anticipation, may not be written into the bedrock of reality. It could be an emergent property, a story that unfolds only because our particular universe started its journey from a singular, silent point of near-perfect order. Our relentless march from past to future, then, is not a universal truth, but a personal inheritance from the first moment of everything, a whisper of that initial order still echoing through the expanding dark. The very act of looking seems to force the universe to make up its mind. In the quantum realm, particles exist in a haze of possibilities, a superposition of many potential states, all described by a mathematical entity called the wave function. This wave function evolves smoothly and predictably, governed by the Schrödinger equation, a law as deterministic as Newton's laws of motion. Yet, when we set up an experiment to measure a property of that particle, something strange and abrupt occurs. The cloud of possibilities vanishes, the wave function collapses, and we get a single, definite answer, a particle in one specific location or with one specific spin. The smooth, deterministic evolution is violently interrupted by the act of observation itself, and the theory provides no mechanism for how or why this happens. This is the measurement problem, a paradox that lies at the very boundary between the quantum world and the world we experience. Why does the mere presence of a measuring device, a camera, or a conscious observer cause this sudden transition from the many to the one? Quantum mechanics gives us the rules for calculating probabilities, but it is utterly silent on what actually constitutes a measurement. Is it the interaction with a single photon, the activation of a silicon chip, or does it require a conscious mind to finally crystallize reality? This ambiguity opens the door to profoundly different interpretations, each painting a radically different picture of existence. The many worlds interpretation offers a breathtaking escape from the problem. It suggests the wave function never collapses at all. Instead, at the moment of measurement, the universe itself branches. Every possible outcome predicted by the quantum math actually occurs, but in a newly created parallel reality. In one branch, you see the particle spin up. In another, an identical version of you sees it spin down. There is no single outcome, only an ever-branching tree of all possibilities, meaning that every quantum event spawns new universes. In this view, the definite world we experience is just our local branch of an infinite multiverse. Other interpretations take the opposite approach, seeking a physical trigger for collapse. Objective collapse theories propose that the wave function is inherently unstable. When a quantum system becomes too large or too complex, interacting with too many other particles, it spontaneously collapses into a definite state. The boundary is not consciousness but a scale of mass or complexity. This would mean that reality becomes concrete not when we look, but when quantum effects simply leak away into the environment, a process known as decoherence. Yet another school of thought, the Copenhagen interpretation, long the standard view, essentially sidesteps the question by treating the measurement process as a fundamental, inexplicable axiom, a black box where the quantum rules stop and classical reality begins. This practical approach has fueled technological revolutions, from lasers to semiconductors, even as it leaves the deepest philosophical questions unanswered. The measurement problem, therefore, is far more than a technical glitch in the equations. It forces us to confront the nature of reality itself. Does the moon exist when no one is looking at it? If our most fundamental theory says particles have no definite properties until measured, then what gives large objects made of those particles their persistent solidity? The problem reveals that quantum mechanics, for all its staggering predictive power, is still an incomplete description. It is a set of rules for what we will see when we look, but not a story of what is actually there when we are not looking. This gap between the mathematical formalism and a coherent physical picture is the last great frontier of the theory. It is a reminder that our understanding of the cosmos may forever be intertwined with the mystery of observation, suggesting that in the quest to comprehend the universe, we cannot fully separate the observer from the observed. The act of seeking an answer may be what creates the answer we find. The cosmic microwave background is a flawless tapestry of ancient light, but its perfection holds a contradiction. This faint afterglow of the Big Bang, visible in every direction, displays a remarkably uniform temperature, varying by less than 1 part in 100,000. Yet, regions on opposite sides of this sky have a temperature that is identical to an astonishing degree of precision. According to the standard Big Bang model, this should be impossible. These distant patches of sky are so far apart that light, traveling at the universe's ultimate speed limit since the beginning of time, has not had nearly enough time to travel between them. They have been forever out of touch, separated by distances greater than light could have bridged in the age of the cosmos. How, then, did these isolated regions agree on the exact same temperature, as if they had once been in intimate contact, exchanging energy to reach a shared equilibrium? This is the Horizon Problem, a paradox that revealed a critical flaw in our story of the cosmos. It suggested the universe we see was never small enough or connected enough to become so uniform through any ordinary process. The solution required a radical rewrite of the universe's opening chapter. The leading answer is a concept called cosmic inflation. This theory proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent a brief, unimaginably violent growth spurt. Space itself expanded exponentially, faster than the speed of light, inflating a region smaller than a subatomic particle to a size larger than our entire observable universe in less than a blink. This process did not violate relativity, as it was space itself stretching, not matter moving through space. The crucial effect was that regions which appear causally disconnected today were once packed tightly together in that microscopic, pre-inflationary seed, able to exchange heat and reach a common temperature before being blown apart by inflation. What we see as opposite horizons of the cosmos were once neighbors, and inflation stretched their shared conditions across the sky. This paradox was not a minor puzzle. It was a glaring inconsistency that forced cosmologists to invent a new mechanism, one that not only solved the Horizon Problem but also elegantly explained other mysteries, like why the universe is so flat and why the large-scale structure of galaxies exists. The Horizon Problem demonstrates a powerful principle in science, an apparent impossibility in the data, a detail that seems too perfect to be true, can become the most compelling evidence for a revolutionary idea. The uniformity of the cosmic microwave background, a fact that once threatened to break the Big Bang model, became its greatest refinement, pointing us toward a stranger and more dynamic origin story where the entire visible universe is just a magnified fragment of a microscopic, perfectly equilibrated beginning. This precise flatness is not a cosmic coincidence, but a clue written into the geometry of everything. The universe's spatial geometry, the very fabric of the stage upon which galaxies perform, is measured to be extraordinarily flat. This is not flat like a tabletop, but flat in the sense of Euclidean geometry, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. Observations from the cosmic microwave background and the large-scale distribution of galaxies confirm this with stunning accuracy. In the standard Big Bang model, this presents a profound fine-tuning problem of almost unimaginable delicacy. The universe's geometry is determined by a tug-of-war between two competing factors: the kinetic energy of its expansion, trying to blow everything apart, and the gravitational pull of all the matter and energy within it, trying to pull everything back together. For the geometry to be perfectly flat today, the density of the universe had to be precisely balanced at the Big Bang, matching a critical value to within 1 part in 10 to the power of 60. That is a 1 with 60 zeros after it. To visualize this level of precision, imagine balancing a pencil on its tip, not just for a second, but for billions of years, with the slightest initial deviation causing it to topple almost instantly into a vastly different state. In an expanding universe, any tiny initial curvature, any deviation from that perfect critical density, would have been wildly amplified over cosmic time. If there had been even a little too much matter, gravity would have won long ago, causing the universe to collapse back on itself in a big crunch. If there had been too little, expansion would have dominated so completely that galaxies and stars could never have formed, leaving a cold, thin, and empty void. The fact that we observe a universe so exquisitely balanced, so flat after nearly 14 billion years of evolution, seems statistically absurd. It suggests our cosmos began with its settings dialed in to an impossible degree of accuracy. This flatness paradox, like the horizon problem, finds its most compelling resolution in the theory of cosmic inflation. The mechanism is elegantly simple in concept. During that brief, hyper-accelerated expansion in the universe's first moments, any initial curvature in spacetime would have been stretched to near insignificance, just as inflating a balloon dramatically smooths out its surface wrinkles. From our perspective within this vastly inflated region, the local geometry appears perfectly flat, regardless of what the microscopic starting condition might have been. Inflation acts as a cosmic iron, pressing out the wrinkles and curves, driving the density toward that critical, balanced value. This single idea does not just solve one puzzle, it elegantly addresses multiple enigmas at once. The same inflationary spurt that allowed distant regions to communicate and become uniform also stretched spacetime to the flatness we observe today. It transforms two separate, staggering improbabilities into natural outcomes of a single, dynamic event. The flatness paradox, therefore, shifts from being a sign of inexplicable fine-tuning to a predicted signature of our universe's explosive birth. It tells us that the large-scale geometry we measure is not a fragile accident, but a direct imprint of that primordial growth spurt, a fossil from the first fraction of a second of existence. This realization reframes our search for understanding. We are not living in a universe that was miraculously tuned at the outset, but within a vast, flat expanse that is the inevitable consequence of an inflationary beginning. The very straightness of space itself becomes a message from the dawn of time, whispering of a moment when everything we know was smaller than an atom, and a force beyond gravity shaped the destiny of all that would follow. Infinite density is a concept that should not exist, yet our equations insist it does. At the very heart of a black hole, according to Einstein's theory of general relativity, lies a point of zero volume where matter is crushed to infinite density, a place where the curvature of spacetime becomes infinite and all known laws of physics simply cease to apply. This is the singularity, a mathematical ghost haunting our most successful theory of gravity. The same ghost appears at the very beginning of our universe, in the initial moment of the Big Bang, where all of space, time, and energy was once compressed into an infinitely dense, infinitely hot point. These predictions are not features but failures. In physics, an infinity appearing in your equations is not a description of reality. It is a glaring red flag, a sign that your theory has reached its breaking point and can no longer describe what is truly happening. The Singularity Paradox is this stark contradiction. Our most powerful and well-tested theory of the cosmos confidently predicts its own irrelevance at the very moments we most want to understand, the birth of everything and the ultimate fate of matter. It is as if a flawless map of a continent suddenly dissolved into a blank, white void at the location of its highest mountain or deepest canyon. The map is not wrong about the terrain it shows, but its silence at the extremes tells us the map is incomplete. This paradox is the screaming engine driving one of the greatest quests in modern science, the search for a theory of quantum gravity. We need a framework that can marry the cosmic rulebook of general relativity with the subatomic rulebook of quantum mechanics. Only such a unified theory could hope to describe what truly happens when gravity becomes so strong that the very fabric of spacetime is tied into a knot. Candidates like string theory or loop quantum gravity offer tantalizing glimpses of a world without true singularities. They suggest that at these extremes, quantum effects take over, preventing infinite collapse. Instead of a point of zero volume, there might be a tiny but finite region of unimaginable density where spacetime itself is woven from discrete quantum threads, like a piece of fabric emerging from individual threads. In string theory, the fundamental entities are not point-like particles but vibrating loops of energy, and this vibration may provide a pressure that halts the infinite crush. In loop quantum gravity, spacetime is not a smooth continuum, but a network of tiny, indivisible units, a pixelated reality that cannot be compressed beyond a certain limit. These theories transform the singularity from a barren endpoint into a gateway to a new physics, a place where spacetime may bounce, tunnel, or transition into another state entirely. Confronting this paradox forces us to accept that spacetime itself may not be the fundamental stage of reality, but an emergent property, a collective behavior of something deeper and more granular. The journey to resolve the singularity is not just about fixing a mathematical flaw. It is about discovering what the universe is made of when both space and time lose their familiar meaning, revealing the quantum architecture of reality itself. These 30 mind-bending puzzles are not a collection of errors in the universe's design. They are instead a map of our own ignorance, each one a brilliant flare sent up from the very frontier of understanding. From the intimate, unsettling question of a cat in a box to the vast, geometric perfection of the cosmos itself, every paradox we have encountered serves the same vital purpose. It is a signal, a flashing warning light that our current map of reality has reached its edge. These contradictions are the precise points where our logic, our mathematics, and our most trusted theories strain, crack, and finally break against a truth we have not yet grasped. They are not signs that nature is broken, but proof that our models are incomplete. This is the true, humbling gift of a paradox. It forces a confrontation. It does not allow us to look away from the uncomfortable, the counterintuitive, or the seemingly impossible. A paradox demands that we choose to either abandon our cherished assumptions or to venture bravely into uncharted conceptual territory. It was the ultraviolet catastrophe that shattered classical physics and birthed the quantum realm. It was the dark night sky of Olbers that helped topple the idea of a static, eternal universe. Time and again, it is the stubborn, inconvenient contradiction that becomes the catalyst for the next great leap. This journey reveals that physics is not a dusty tome of settled facts. It is a dynamic, living dialogue with the cosmos, a conversation punctuated by these profound questions. Our intuition, forged in a world of medium-sized objects moving at slow speeds, is a poor guide for the extremes of the quantum scale or the cosmic horizon. These paradoxes systematically dismantle that intuition, training us to see the world not as we expect it to be, but as it actually is. They remind us that reality, in its rawest form, is under no obligation to make sense to our human minds. The universe operates by its own sublime, often bizarre logic, and our task is to learn its language, one paradoxical clue at a time. What feels like a flaw in our reasoning is often the first glimpse of a deeper pattern, a hidden symmetry, or a new dimension of existence waiting to be discovered. So we should not fear these puzzles but celebrate them. They are the growing pains of a science that is always reaching, always questioning, always becoming more than it was. They are the evidence that our quest to understand the cosmos is alive and thriving, driven forward by the very things we cannot yet explain. In the silent spaces between the stars, in the ghostly haze of a superposition, and in the infinite density of a singularity, the greatest mysteries and the next revolutions are patiently waiting. Our journey through these 30 contradictions is more than a tour of cosmic curiosities. It is a testament to a universe that refuses to be easily understood, a realm where logic itself must bend to accommodate a deeper, stranger truth. These paradoxes are the fault lines in our understanding, the brilliant cracks through which the light of a new reality begins to shine. They remind us that science does not advance by accumulating comfortable facts, but by stumbling headlong into impossible questions that force a complete reimagining of the world. Every great revolution in physics, from the quantum to the relativistic, was born from precisely this kind of bewildering contradiction, a moment where the old equations broke down and whispered of a landscape beyond the map. So when you encounter a paradox that twists your mind into knots, do not turn away in frustration. Lean in. That discomfort is the feeling of your understanding expanding, of old assumptions crumbling to make space for a grander vision of reality. It is the universe inviting you to look closer, to think deeper, and to participate in the greatest detective story of all time. Which of these 30 puzzles lingers in your thoughts, challenging everything you thought you knew about time, space, or existence itself? Share your reflections in the comments below and let us continue this conversation. For more explorations into the heart of cosmic mystery, be sure to subscribe. Thank you for joining this voyage to the edges of understanding. Keep questioning, keep wondering, and above all, stay curious.